of the body is standing on the ground. The chassis effectively is a six-legged walking machine. So what happens in this performance is that by lifting one leg up, 3 robot legs lift and swing forward. By lifting the other leg up, the other 3 robot legs lift and swing. So it's possible to generate a walking movement through this more direct coupling of the body. Also, we used pneumatic rubber muscles. Now, this robot was 5 meters in diameter. If you imagine a steel cylinder weighing 12 kilograms and you want to use 20 of those cylinders, that increases the weight of the robot immensely. But by using rubber muscles, a rubber muscle this long is only about 500 grams with the aluminium couplings at the end. So it works like an anatomical muscle. 1 bar of air pressure, the rubber muscle acts like a spring. 7 bar of air pressure, the rubber muscle expands in girth, contracts 20% of its length, producing a strong pulling force. So the result is a robot that can be very large but relatively light. This 5-meter diameter robot was 200 kilograms lighter than the 3-meter diameter exoskeleton robot. So the rubber muscles made a huge difference. And also, it was this kind of choreography of contracting and inflating muscles and exhausting and extending antagonistic muscles that resulted in the robot moving. This is a small 2-meter diameter robot which is called the walking head. It's a kind of a chimeric structure, a human head with an insect-like body. It has an ultrasound sensor that detects if someone is in the room. When someone is in the space, the robot stands and begins performing. Can we have the sound for this, please? So the robot basically then sort of goes to sleep until it detects another person who comes into the gallery. It's still a work in progress, but the idea of this is to turn it into an actual virtual system. So the behavior of the human face is actuated and modulated by the mechanical movements of the legs. Also, at the moment, the head is an animation on the onboard computer, but it could be a head that's transmitted over the internet, so you could have a 6-legged walking robot as your body in some other place. Sound for this, please?
In the Biologically Inspired Robotics Laboratory at Case Western Reserve University, our near-term robots use abstracted insect locomotion principles, whereas our advanced legged vehicles are more directly based upon insects. Both of these lines of vehicles can be scaled up or down in size to suit specific mission requirements. Our larger near-term robots use 6 appendages driven by a single motor in a nominal alternating tripod gait like that used by insects. The 3-spoked appendages, called wegs, combine the speed and simplicity of wheels with the climbing mobility of legs. Their wegs are compliant so that their gaits adapt to the terrain in a cockroach-like manner. These mechanisms enable the robots to traverse terrain and climb obstacles that would be difficult or impossible for a wheeled vehicle to navigate, at speeds currently unattainable by any legged robot at this scale. A body flexion joint, also found in cockroaches, enables our WEGS robots to surmount more complex obstacles. The compact mini-WEGS uses 4 WEGS in an alternating diagonal gate to sustain speeds of up to 10 body lengths per second over smooth and rough terrain. It uses only one motor to drive the WEGS and one microservo for steering. Its lightweight and robust construction allows it to sustain repeated falls from a height of over 10 body lengths and tumble down a flight of stairs with no damage. Crickets and click beetles use jumping to surmount obstacles of immense relative size. A version of mini-WEGS has been developed based on this concept. It can surmount obstacles 2 to 3 body lengths in height. It reviews unmanned ground vehicles.
Okay, so I showed this. The lead researcher is Dr. Roger Quinn at Case Western Reserve University, but I show this as an interesting hybridization of wheels and legs so that this little robot can move very fast in a smooth terrain, but also can walk over obstacles with its sort of spoked appendages. And it's very, very interesting that they also use pneumatic rubber muscles in their sort of larger insect-like structures. So, for me, a zombie is a body that performs without a mind of its own, that performs largely involuntarily. A cyborg is a body, a hybrid human-machine system that becomes increasingly automated. We have always feared the involuntary. We've always been anxious about becoming automated, but in fact we fear what we have always been and what we've already become. We've always been zombie bodies without a mind of our own, and we've already become cyborg bodies, prosthetically augmented bodies, in becoming this extended operational system. All of these body constructs up until now have been using kind of hard technologies. In this project titled Blender, in collaboration with another artist, Nina Sellers, both artists underwent surgical procedures to remove 4.6 litres of biomaterial, and this biomaterial was placed in an installation in a sealed container. The compressed bottles of air, once every 5 minutes, activated the blender blades, blending the biomaterial from the two artists' bodies. This is kind of the inverse of the stomach sculpture. Instead of a machine inside a soft body, here a liquid body is encased in a machine installation. It's also somewhat anthropomorphic in size. It's about human height. And this is a collaboration that did not result from the addition of each artist's ideas, but rather from a subtraction of each artist's physical body.